what you tell us today.
Okay, so hello everyone. I want to give you a short insight into my bachelor thesis about passenger transfer. This we have already seen. Now to the presentation. First, I will shortly show you the state of the art in terms of transfer into the tube. Afterwards, the problem and task of my bachelor thesis, my approach, and in the end, I will show you 2 examples. To show you the state of the art, I brought you a few pictures from already implemented transfer systems. On the left, you can see a docking mechanism, which is used in space. In the middle, there is a typical door for a submarine. And on the top right, there is a passenger transfer in an airplane, as you probably know. And on the bottom right, there is a picture from a metro, you'll also know. To show you the state of the art in terms of Hyperloop, I brought you a picture from Virgin Hyperloop 1. They have already implemented one solution. As you can see on the left side, there is a long tube and an airlock, which divides the right section apart. This section is the airlock chamber, which can be floated with air. And afterwards, you can just open the door on the right side in the picture. Now to the problems with vacuum, you have, as you can see in my figure, you have air pressure inside of the vehicle and also outside of the tube. And between there is this partial vacuum, which causes huge forces and which also needs energy to create it. And if passengers come in touch with this, it's of course fatal. The question is therefore, how can the passenger come from the station into the tube and into the vehicle? I searched for a technical solution which is efficient in terms of energy, costs, and so on, and also high speed. Of course, it also should be secure. To solve these tasks, I have planned the following work packages. First, collecting informations and ideas, and then building concepts and evaluate these concepts and to pursue with 1 or 2 further. Afterwards, I collect the critical functions and try to test and visualize them. And at the end, evaluation and outlook, which is an important step since my thesis is a concept study and it builds therefore the basic for further projects. After researching, I organized a workshop to collect creative and broadly conceived ideas. I clustered them into 2 big mind maps, as you can see one of them here. Then I listed all substeps of my on-offboarding process in a morphological box and tried to fill it with the creative ideas. And afterwards, I created concept, evaluate them, create a new, and so on. Now I will show you the evaluation criteria I used. But first of all concept has to be realizable, since the project should be realized until 2026 in the beta tube of EuroTube. Now to the evaluation criteria, the system shouldn't be complex. It should be high speed and efficient in terms of space, material, and stuff. It also should be low energy consumpting. Self-determination for passenger. This is meant how far can a passenger determine what happens to himself. So if you're going on a roller coaster, you can choose whether you really want to go on this roller coaster until you're standing before it. But as soon as you're sitting inside and it starts, you're not able to say, stop, I want to leave. Then another criteria is the comfortability in technical, with technical meaning. It's independent of things like seat equipment and so on. And in the end, security for sure. The detailed evaluation consists of every possible sub-step and variation of the process. As you probably can imagine, this results in a huge document. Therefore, I decided to just pick 2 of the about 10 systems and present them here. This is also the state-of-the-art I'm currently working on in my bachelor thesis. The concept 1, as you can see, I've always made this little comic stripe to describe every little sub-step. The first concept is a lock on the vehicle. This is similar to an airlock, but it's not next to the vehicle, but it's a lock onto the vehicle. So there is less space used, space which you have to float with air and afterwards rebuild the vacuum. And this lock on the vehicle can be realized with a clamp mechanism or possible with a mechanism like an Aris, which you can see on the bottom right side. In this concept, the vehicle stays in the tube. So the doors are on the side of the vehicle and on the side of the tube wall. Now to the rest of the passenger transfer, which is probably more intuitive. The process is based on a technical device like a smartphone or whatever is used then in 2026. With this, you can book your seat and locker, and then you're guided with the smartphone, and you can open your compartment for your luggage with this smartphone, and so on. To give you the feeling, I have listed 3 pros and 3 cons of the concept. Please note that this isn't the whole evaluation. These are just 3 positive and negative aspects. First, positive is that there isn't that much energy used for the vacuum. Also, it's efficient in space and time, and you have a separate section with atmospheric pressure, not only a little bridge for the passengers. Negative is that the passengers have to lift their luggage themselves, which is probably not that comfortable. Also, it's a rather complex docking mechanism, and also the doors could be rather complex because these doors are on the tube wall and on the vehicle and need to withstand these big forces from the vacuum. For this first concept, I have a variation, a drawer system. In this system, the passenger don't walk into the vehicle, but they're sitting outside on a seat model like you can see here in green. And then the seat models are pushed in, so you have a better use of space. This is, of course, also usable for the luggage compartments. Now we move on to the second example. Some of you probably already heard of it. It's a dock at the end. First, the nose part of the vehicle has to be lifted away so that the passenger cabin directly dock on the end of the tube. And then the 2 doors, as you can see in the pictures, can be opened. In this concept, there isn't any vacuum that needs to be floated with air. The rest of the system here is similar to the first concept, so I left it out. Now to 3 positive and negative aspects. As already said, there is no energy needed to rebuild a vacuum. There are no such big doors on the side wall, and also it can be a good combination with seat models. I will just show you afterwards. Negative is that it's a complex design of the vehicle because the nose has to be lifted upwards or other way. Also, it has a small entrance, and it's only possible as a terminus station. So the vehicle has to drive afterwards in the other direction. It's not possible that the vehicle drive through the station. Now to these seat models. Here is probably useful to use these models, which are pushed inside the vehicle. So the passengers sit down on the outside and then are pushed inside. So they don't have to walk inside this small entrance. These were two of my concepts I wanted to share with you. Now I have some last words. To the questions, the concepts are at the early stage, so I probably don't have a perfect answer on every question, but don't hesitate to share your critical thoughts, because this is exactly what I'm going to work with in my next step. Generally, I want to recommend a thesis connected to a real-life problem like this one. And if you're interested in a vacuum transportation, please go on the website. I wrote it also on the slide. There are already a few theses proposed, but if you don't find one for you, just contact Fabio from Eurotube or Natalie from Swissloop, and I'm sure they will be glad to help you. So this was it from my side. Thank you for your interest. Yeah, I think we can move to the questions.
Thank you very much, Simone, for the insight in your concept study with all those nice drawings and then also very large variety of concepts. Yes, please, Natalie, can we go and have a look at the collected questions? I see there's already some. Please also use the +1 to upvote questions that you like. We don't hear you currently, Natalie.
Sorry.
Now it's better, thanks.
So the first question is, does the docking mechanism in space face the same vacuum/sealing challenges?
Of course, they also have this problem with the sealing in a different, in a exactly opposite way. But I think there is a big difference, because in space there is all very slowly, and you have to be very exact. And this is the problem in space. So if you not quite right, you crash in the spaceship and in the space station and so on. This is so it's other problem in the space than in Hyperloop. In Hyperloop, it's exactly the opposite. It shouldn't be as slowly, but it should be very fast. So the vacuum technique is probably similar, but not the solution of transfer.
Mm-hmm.
I hope this answered the question.
I think maybe the question was also related to the sealing part, maybe the transition from the airlocks.
I think they also have a kind of airlocks. I think these can also, their system there can also be used for the Hyperloop system. But as already said, this system is for another purpose, for a slowly and precise purpose, and not for a fast purpose, as Hyperloop.
Mm-hmm. Okay, the next question is, which substep is the most critical function?
There, I think the most critical one is just to make this connection to the pot. So how is the vacuum handled? There are solutions like you can take out the vehicle, and then it's the substep how you get this vehicle outside. And if you have the systems like you leave it inside, then it's the part of how do you make this bridge inside to the vehicle. Okay. I think this is the most critical one.
And the next question is, what was the most promising docking mechanism and why?
This is an answer right a bit before where I'm just currently working on, so I can't have a precise answer on this one. I just have showed you the two most preferred systems in the evaluation we did already, but these aren't my final thoughts.
Then the next question is regarding the second concept that you talked about. And the question is, how do you apply the horizontal force so that the pod is not being pushed back in due to pressure difference?
Sorry, I didn't get this right.
So in the second concept that you proposed, the question is, how do you apply the horizontal force so that the pod is not being pushed back in due to the pressure difference?
Okay, yeah. This is directly on the mechanism in the front, but this mechanism exactly isn't already implemented, so I don't have this mechanism, so I can't answer this already. Yeah, but I know it's a big problem, these forces. Yeah.
Then the next question is, what was the most promising? Oh, that we already had that, so the orders are changing. You mentioned comfort. How do you imagine a comfy seat in a pod? How a comfy seat in a pod would look like? Does it look like a normal train seat?
As I already mentioned, I mean comfortable on technical side, not on equipment. So for me, it's not comfortable, for example, the doors in the submarines. So you have to go there, stairs down and so on. This isn't comfortable. But if you're on a train, you just walk. This is a comfortable way. Or in the example I've showed you, I have this locker system on which you don't you put your luggage into these compartments by yourself, and this is probably also the technical aspect of comfortability. I hope it's clear now, this evaluation criteria.
Mm-hmm. The next question is, what are the current thoughts of HTT, Virgin Hyperloop 1 or HART regarding station design? Will there be a need of a design where the pod moves in one direction?
They don't have already designs there, are they have on their website or so on. So they haven't anything implemented. All the only thing is actually implemented is the picture I've showed you. But I think this is also not their last solution. This is only a solution for testing. So the further project from them, I don't know. Yeah.
Mm-hmm. Next question. How would you quantify the energy consumption you mentioned in your pros and cons?
The energy consumption is quite difficult to really quantify, but I don't know if you were in the seminar where they talked about the vacuum pumps and so on. These need enormous energy, and so this is a very big. This has very big impact, the volume of vacuum that you have to create, and because of this is a good criteria to compare. On this point, I have to say, because all these concepts weren't already implemented, and also already implemented, I have to evaluate them and to compare them and not say, okay, it's exactly such and such much energy used, because this can't be said on the state I'm currently at. For this, all the system has to be more precisely.
Mm-hmm. The next question is, how important is an important docking mechanism to realize a satisfying customer journey? Is it even possible to compete with other transportation modes?
I think if a Hyperloop is only able to compete with others if it is faster and comfortable. Not when you're this. The goal is to take these short-term flights and make them faster. So if when you're flying, you have to wait and you have to go inside, and the whole process takes a lot of time. So if you can short this time, you will save enorm of your time for the journey. And I think this makes the Hyperloop to a good concept. We can compete with the existing systems.
I think we have time for one last question, and then we will switch.
Yes, there's one question left on Slido, and then another. Okay, so the second last question is, what are your thoughts on evacuating the whole pod? It seems like this would be much safer.
Yeah.
Yeah.
I totally agree. The thought is that you need a more enormous space which you have to evacuate afterwards, and therefore it's use enormous of energy, and also this creating the vacuum takes a lot of time. So it's time and energy consumption which led to these solutions I've presented now. But I totally agree that in terms of safety, it's safer to just take the whole vehicle outside of the tube.
Mm-hmm.
Great, thank you very much, Simone. Then we will do now a switch to Manuel. He will present a cooling method of a long stator linear motor. That's his master thesis.
Yes.
Good, then let me start. This one I can skip, it was already said. Then first I will introduce myself for everyone who don't know me. My name is Manuel Häusler and I'm a master student at HASLU, at Fachhochschule Luzern. Some of you see me already in the first seminar when it was back in ETH. All the others, you can see me now on screen. That should be enough. I want to mention, I don't want to go everything you see here on the screen, but for the contact, if you have further questions that I can't answer here, or do you want to need help from me or everything, please contact me. I'm on my website or one of my email addresses you can see on this slide. Then I think I will go forward so we can go to the technical aspects and not bothering you with these kind of things. The content I will present you is about dynamic systems. It was announced that I will tell you about the cooling system. The cooling system will come on the last few slides about the example. Thermal aspects on a Hyperloop system is always coupled with dynamic systems and multi-domain and multi-physics systems. That's why I will start with these topics and come to the example of Hyperloop at the end. There exist two main modeling approaches these days. One is the detailed study of one specific component. You know this from finite volume methods or finite element methods, where you apply partial differential equations, in other words, you apply a field theory on some discretized elements to optimize or to analyze one specific component of a system and get spatial roomically solutions where you can optimize very specialized or very detailed. And there exists another type of modeling approaches that I will say it's a system kind of modeling, a network kind of modeling, where you don't look at one component, but on systems as a whole. And there you apply ODEs, so ordinary differential equations, analytical formulas, and measured correlations, and to build or to model a whole system and how it is responding to some kind of input signals. A very common name for that is building a digital twin. So you are building a twin of a system that is as accurate as possible and as easy formulated as possible, so it is very performant, and you can do lots of simulations and optimizations to get the whole system working better, optimizing in energy or whatever. And that's why coupled dynamic systems. So we don't want to look at one specific component, but at a system as a whole. I can show you an example how such a model could look like. This one is a model of a hydraulic system of a tank, which is pumped in and flooded out. And then you get a response of the system, which you can optimize by some controller variation, so that the system as a whole will be optimized. And yeah, that's the whole point of doing system modeling instead of component modeling with CFD or some other things you might know. Yeah, so to mention a couple dynamic systems, they are defined as initial value problems in a mathematical way with ODEs. And here you can see a little example of such a system model of an equivalent circuit with a resistance and an inductance in the electric domain. And this kind of solutions are done by solving it with time integration. So you have some formulas, some differential formulas, some algebraic formulas, and then you will do a time integration and get a solution for a specific starting value, and then you can plot the output of the system as a whole. This set of differential and algebraic equations are special because they are always exchange energy, mass, and momentum. So these are the quantities which are conserved, and that's in every kind of physical domains. So it is in mechanical, it is in electrical, in hydraulics, in thermal, everywhere these kind of states and variables are conserved, and that's why we can do couplings and do and can model systems that are facing the machine as a whole. there exists a very handy theory or approach to solve this kind of problems. It's called bond graph theory or system physics. I don't know which one do you prefer. It's another approach to look at physics. So there exist, I mentioned here three kind of ways you can look at the physics. This is the point mass mechanisms. So the quantities there have no room dimension, and a common formulation for that point mass mechanics is the common formulation of Newton. So F is m times a, force is mass times acceleration. There you don't have any room information, you don't have any flow quantities, or it's just one component with no room dimension. Then there is another approach, the continuum mechanics. You know that maybe from the Navier-Stokes equations or from the Lagrange approach of mechanics. There you don't have a small point where all the mass is in. There you have fields and continuums where you quantify the quantities and the variables, and you get a field of solutions and a whole stack of solutions out of this kind of analysis. And then there is the third one, that one that I use for my modeling approach. It's the state space approach. There the quantities are treated as flows and potentials. So you have a potential that will drive a flow of a specific quantity, and therefore there you have a state space representation. The core feature of this kind of looking to the physics of the system, or the system physics, is the tetrahedron of states you see on the right side of the presentation. You have a flow of a quantity, a momentum of a quantity, a potential of a quantity, and you can connect all these states and variables with some correlations, and you get a model domain out of it. I will show this on a few examples. Maybe you know the electronic domain. That's the one you maybe learn in bachelor also. So there you have one quantity that defines the modeling domain. Here in the electric domain, it's the charge. It's the electron or the proton. And then out of this quantity, you can have a flow. In the electric, it's the current, so it's a charge that flows, or is a derivative by time, so it flows by time. You get amperes. Then you have a potential that drives that flow. In the electric domain, you have there the voltage. So you need a potential to get the quantity to flow. And that's the connection in the tetrahedron of states that will connect the charge with the current and the charge with the voltage. And then you have all the other states, momentum. You have resistance that gives you a resistance to the flow. You have a potential storage. In the electron, you have the inductance, the capacitance, and you can do this on nearly every domain you like. So you can choose a quantity, and then you have to do the rules which are stated here. you define a variable E, a flow variable F, and a quantity Q, and then E and F together should be a power, and then you have created a new modeling domain which can be used for this kind of modelings, as for coupled dynamic system modeling. I do this kind of modeling with the modeling language Modelica that is excellent suitable for this kind of modeling, and it's suitable for this system physics approach because of these points I pointed out here. For example, equations are you define the correlations with equations instead of assignments. In a normal programming language, you will assign to a variable, like x is assigned to 2.2 plus y. In an equation, you would say x plus y is 3 times z. There it is multidirectional, so it doesn't matter for which variable you're looking for and which one is given. Then it is port-based modeling. You can define ports where your flow variable and your potential variable can exchange to the next model, and therefore you can build up your models on component for component until you have a complete system model. It's object orientated. You have variables. You can give attributes. So you can give every variable a unit, for example. In other languages, you will have just a real, for example, a real type or an integer type or a Boolean type. Here you can specify your own type, for example, the temperature type, which is in this case type real with unit Kelvin and should be displayed in degrees Celsius and so on. You can define a lot of attributes that helps the solver to solve your problem. And that's an example how such a model could look like. It is a resistor. Yeah, I will skip that. And also this slide, that's some implementations of Modelica. If you're interested to build your own models with Modelica, these are programs to do it. But now I will come at least to the example. So what I'm doing in Hyperloop, it's a system model of a cooling system for different components that should be cooled inside the system. And why do I use such dynamic systems? Because Hyperloop thermal systems are always multi-domain problems. Why? You see the 3 points. Why? You have always the electrical components that suffers from the Joule effect. So when they conduct electrons, they will be heated up, and the conductance of a hot material is lower than of a cold one. So you couple the thermal domain with the electrical domain with this Joule effect, and therefore to analyze the thermal domain, you have to analyze also the electrical one, and vice versa. So it's a coupled problem. And also because we are using induction motors, namely the linear induction motors, they suffer from end effects. And these end effects are coupling electrical and mechanical domain, because end effects are scaling with the speed of the vehicle. And if your vehicle is fast, you will have more end effects and more losses due to end effect in the limb, and therefore the limb will be heated up more when there is more speed. So you have a coupling in electrical and in the mechanical domain because of that. And last but not least, the cooling circuit is flooded by some kind of refrigerant or water or whatever, and the heat inside of this fluid is transferred by convection, and convection is always a coupling between thermal and hydraulic domain. So you have the fluid dynamics, who defines how the flow is flowing, and you have the thermal aspects, how the heat is coming into the flow. And that's why you have to study the thermal aspects always as a system-wide problem with couplings. And this kind of questions I like to answer with my models I'm actually doing in my master thesis. For example, you can read it for yourself. I thank you for watching and hearing, and do you have any questions?
Thank you very much, Manuel. A very nice introduction into Modelica, multiphysics modeling and simulation. I have several questions. I need to type them in, or maybe I will contact you later. Yes, let's go over to Slido. We have 12 minutes left, so please type in your questions right now so that Manuel can answer them. Can you, Natalie, take it over again? Currently, we don't hear you.
Sorry. The first question is, what are the limitations to the system physics approach?
Limitations. I think the biggest limitation is always the assumptions you make during modulation. So you wanted to have a good digital twin, so a model that corresponds to your system as much as possible, but on the other side you want to have a very performant model that you can do a lot of simulations, and this is important for optimization. You have to do lots of simulations to choose the best one, and therefore you have to do performant models instead of very accurate model. It should be accurate, but not very detailed. It should be fast. It should cover all the important features, but not go into too much detail. So I think the biggest limitation is the approach you choose. How detailed do you model, and on the other side, how performant you want to model.
Okay, thank you. The next question is, why did you use the state space approach for your thesis and not one of the others? How would the outcome be different with other approaches?
I think I choose it because of the performance reasons. The state space approach is mainly a 0D approach, so with no room dimensions. And because you have no room discretization, it makes your model very fast. And that's the main point. I use this kind of approach. And on the other side, you can analyze the couplings between the components of the system, which is very difficult in the other kind of approaches like FEM or CFD. You can do it, but it will take a lot of resources to calculate the results. And with a state space approached model, you can do this in a much short time with very good results, but also with high performance.
Okay, thank you. The next question is, why are there only the end effects connect mechanical and electrical domain? Why doesn't the whole limb?
Maybe I I didn't mention that very good. I am looking at the main part to the thermal aspect of the system. So what I'm interested in is which component to produce heat and which component has to be cooled. And you're right. There are other couplings of the limb with the mechanical domain, but for my interest, it's just the coupling of the end effects, because the end effects are producing heat and on the same time are related to the velocity, to the speed, and therefore that's the coupling what I'm interested in my model.
Mm-hmm. Then the next question is, why did you choose Modelica? What are alternatives?
In principle, you can use every programming language you know to make this kind of models. But I choose Modelica for this specific points I had in my slides. These are 1, 2, 3, 4, 5, 6 points, and I think with this kind of modeling language, it is very easy to do this multi-physics, this bond graph approach. With other languages, it is also possible, but I think it's much easier with Modelica.
Then we have another question regarding Modelica. The question is, can you also do HIW, meaning hardware in the loop control with Modelica?
I heard of that. I think you can do it, but I have never done it, so I can't confirm that it is possible. But I think there are people in my Kompetenzzentrum where I was working, and they did that. I think that's possible.
Okay. The next question is, aren't causalic models more performant because their solving is unidirectional?
Could be. I haven't done a test regarding this especially. But for my side, or for my opinion, it's very handy to have equations instead of assignments and no predefined data flow direction, because you can use the same model for different problems. You just have to connect the ports in the other way, and therefore the Modelica compiler will compile the whole model on a different way, and your output is completely different, but you're using the same model, and the model describes the same component. For example, for the other flow direction, you don't have to recode your whole model, because something very small is changing inside your problem. You just have to connect the ports different, and Modelica will take care of the rest.
Mm-hmm. Okay. The next question is, how are the physical connections / flows translated into a numeric procedure? Is it a nonlinear system of equations in the back?
It depends on your equations, or the set of equations you use to describe your system or your problem. Sometimes there are a nonlinear set of equations that have to be solved nonlinear, but if they aren't, they won't be doing it. So you have here in this slide I just opened, you have there the steps the Modelica compiler uses to compile and run your model. And there is the step of arithmetic simplification, where your whole code is analyzed and parsed and done an arithmetic simplification. So your whole equations will be changed and optimized for better performance, and therefore it's very difficult to answer this question for me, really.
Okay, and then the last question there is on Slido is, how performant is your approach? How are you using the model in the Hyperloop system? And if you can say something regarding optimization.
I'll say it's very performant if you don't have any arithmetic loops. So it's possible that your problem is self-contained. So you need some input information that is generated by the model itself, and therefore it needs algebraic loops. And if you have this one, it really slows down your model. But we are not talking here about days or months to solving a complete system of a Hyperloop. We are talking about seconds or maybe hours. So if I'm talking about a simulation that runs very long, I think about hours to take to simulate, and not like in CFD where it could take days or even weeks or months to solve a special problem. And that's why I'm using this approach, because I can do a lot of simulations and can compare which one are the best, and therefore it's optimal for optimization of the system. So my outcome will be an optimized solution for one kind of system.
Mm-hmm. Okay, so those were all the questions. Thank you very much for answering them. And also,
and if you have any other more, please contact me on my website or my email. Feel free.
Thank you very much, Manuel. It was a great presentation. Also, thank you, Simone. It was also very good. I think we will have a quick announcement from Natalie now.
Exactly.
For the next time. And please stay updated via the website, swissloop.ch research. I think as far as I know, we have 2 sessions left. Is that correct, Natalie?
This is correct, yes. Right. And now a short announcement from Swissloop. We are now approved to be again a focus project for the next season from the Department of Mechanical and the Department of Electrical Engineering at ETH. So for all the students who are currently enrolled in their 4th semester of mechanical or electrical engineering, there will soon be more information announced from DEMOFT, but only to provide you already with some information. There's going to be a Zoom information event on May 11th from 12 to 1. That's a Monday. And in case you're interested to do the focus project, feel free to tune in, and there we provide you with all the necessary information and you can ask all your questions. You can also just shoot an email to info@swissloop.ch if you have questions. And you can check our website, swissloop.ch/focus project. For all the focus projects, the application deadline is May 31st. And well, that holds for all the focus projects. For the application, you need to hand in a CV and a letter of motivation. And yes, so we would be looking forward to seeing the 1st semester students from mechanical and electrical engineering at the information event on Zoom on Monday, May 11th from 12 to 1. Good, so I think that was it from the seminar today. Thank you very much for everyone who tuned in. And also again, thank you, Simon and Manuel, for the presentations. And we're looking forward to the next seminar in 2 weeks on Tuesday evening. Take care, everyone. Stay safe and goodbye.